This is lecture 14 of CS47, Computer Organization Study. This is the second part of the Boolean algebra. In first part, we did talk about in lecture 13 on the recap of Boolean algebra, logic algebras, and defined a Boolean function and its two different form of representation. First form is a function represented as a Boolean expression, and second is a function represented as a truth table. We also discussed how we can convert from Boolean expression to the truth table, and also given Boolean expression, how can we optimize or minimize that expression, and we discussed why we need that. Now, this part will be focusing mostly on how can we derive an optimized Boolean expression for a function represented in a truth table. To do that, first thing we need to understand is standard forms. There are two types of standard forms. One is called sum of product, referred as a SOP, and product of sum, another term that is called POS. So standard forms, two type of standard form, SOP and POS. The purpose of the standard forms is basically represent very large expression in very compact form, right? And then of course the major contribution of this standard form is to facilitate simplification process. We'll see that. But first point, let me elaborate this first point. Why do we need a compact form? So far, we have seen as examples and others as a Boolean function of only handful of variables, like 2 variables, 4 variables, 5 variables, right? And if you see, possible number of terms actually gets increased by power of 2 as we increase number of variables. So it's very often in very large problems there can be like number of variables in order of hundreds or thousands, and in that case the number of terms in the expression can be huge. So we want to have some standard notation so that we can represent the function in expression form in a very compact way. How do we do it? To understand that, we need to understand two terms, and we'll focus on the mean term, but we also need to know something called max terms. Okay, so these are the two type of terms, Boolean terms, mean term and max term, used in SOP and POS respectively. So mean term is used in SOP and max term is used in POS. So mean terms by definition are the product terms containing all the variables of that given function appearing exactly once in their complemented or uncomplemented form. Okay, so mean terms need to involve all the variables. Variables can be either its complemented or uncomplemented form, and they will appear exactly once. You cannot repeat the variable in that term. Then it calls a mean term. Max term is similar definition, but it's a sum term containing all the variables of the function appearing exactly once in their complemented or uncomplemented form. At this point, let me also explain this product term and sum term. What do we mean? We don't have a product or sum operation in Boolean algebra. We have and, we have or, right? So if you recall, and is represented, the function is represented as dot, right? That operation is represented as dot, and sum operation, or operation represented as plus, right? So dot in a normal algebraic sense is product, and plus in normal algebraic sense is sum. So in that way, it picked up these term like product terms and sum terms, product operation and sum operation. And in Boolean algebra, if product operation is mentioned, it really means AND operation, and if sum operation is mentioned, it really means a OR operation. Now, given a truth table, okay, so first let's focus on the truth table, okay, forget about this fourth and fifth column. So your truth table really has three variable x, y, z, and you have some function at the last column. That function is defined, and we have, like, for three variables we have 8 possible combination, and for all combination the function is represented with either 1 or 0, the outcome of that function, right? That's the truth table representation of a Boolean function. Now, for each of this row, we will try to write its product term. Okay, how we write it? We write for the SOP like minterms. We write this way: if that corresponding variable is 0 in that row, we write its complementary term, and with other variables complement or uncomplementary term. So if there is 0, it's complemented of the variable. If it is 1, it is uncomplemented form of the variable. So for example, the very first row, like 0, 0, 0, since x is having value 0 here in this row, we write x bar. Y has value of 0, we write y bar. Z has value 0, so we write z bar, and they are ANDed. So that becomes the product term for that row. Similarly, very last row has all variables x, y, z has value 1, so we write x uncomplemented term for, since it is having x as having a value 1, y also having a value 1, so we write y, and z also having a term having 1, then we write z, and we AND them. So corresponding product term for and combination 1, 1, 1 is x, y, z. A similar fashion we can pick up 1, 0, 1. Let's pick up this one, 1, 0, 1, x1, x term x, y0, so we write term as y bar, and z is 1, so we write z, and we AND them. So 1, 0, 1 corresponding product term is x, y bar, z. Now for each product term we assign some Minterm symbol. Okay, it's usually denoted as a lowercase m with a suffix of an integer number. Okay, like m0, m1, m2, m3. Now what are these? These indices or suffix, that value, suffix value or indices of this symbol small m is basically your decimal value combining three values of this variable. Like for example, third row, let's take the third row, first, second, third. Third row's xyz value is 0, 1, 0, which is 2 in decimal. So its corresponding Minterm symbol is m2. Similarly, 1, 0, 1, its corresponding decimal value, 1, 0, 1 combination is 5. So we write m5. So that means this function's sequence of variable and how we write the truth table, that sequence has influence on how that suffix will come to be. Especially the most important part is this sequence of f followed by xyz. Now if I would have written something like fzxy, these symbols will be changed because I will be writing down the number values in the sequence of z, x, y. So different combination will become different names. So that's what I mean. This once you start writing down these symbols, Minterm symbol, please pay attention to the sequence of variable in that function definition. Is it, what is the sequence, like is it fxyz or is it zyx? It depends on that. Your symbol meaning can vary. Now, how it help in compacting the Boolean expression form of that given function? So from a truth table, okay, we can write this fxyz in this Boolean expression term as x bar y bar z bar, or x bar y z bar, or xy bar z, or xyz. Now, how am I picking up this term? I am picking up the product term from those row which has function value of 1. The function outcome is 1. I'm picking up those rows product term and making a OR between those product term. So I need to pick up this very first row, which is x bar y bar z bar, or I need to pick up the third row, which is x bar y z bar, or I have to pick up the sixth row, which is x y bar z, or I have to pick up the last row, like 8th row, which is x y z. So that's why I picked up those product term corresponding to those row which has a function value of 1 and OR between them. That is one Boolean expression. Now we can represent in terms of symbol, because each of this unique product term has a unique symbol. So I write down this same function as m0 or m1, m0 or m2 or m5 or m7. Then once I have this, I can represent the same way with a sigma symbol. Sigma is basically stand for summation in normal algebra, but we are using that here as well, the sigma m, and simply list down the suffix or indices of these minterms. So this becomes sigma m 0257. So fxy, if I write directly as sigma m 0257, that means I'm talking about ORing between the minterm 0257, and then we know definition of each of this m0, m2, m5, m7. We can replace them with a real product term correspond to that minterm symbol. How is it helping in compacting? Think like you have 100 variable in a function. So you can practically have 2 to the power 100 different combination or 2 to the power 100 product term, and out of that you can possibly take, let's say, 2 to the power 5, like 32 product term, right? So writing the 32 product term with 100 variable minterms is really long. It's painful, right? Instead of that, you can just write, let's say, sigma m 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 till 31, right? And that becomes a very compact representation for this function. So that's the power of like standard expressions, standardization of Boolean expression forms, and this is your sum of product form of Boolean functions. Similarly, we can talk about product of sum. Is a similar concept. So we have the truth table, okay, and we have the function. Okay, this truth table and the function outcome, that's the truth table. Now we are trying to define the sum term for each row. Now it is defined in this way. If my variable is 0, I write its uncomplemented form, and if a variable value is 1 in that row, I write the complemented form of that variable. So for example, the very first row, I have 0 for all the variables, so I will write uncomplemented form of each of these variables, which is x, y, z, and I will OR them. Instead of and, I'll OR them for the sum term. So it becomes x or y or z. Very last row, similarly, all of them has 1. So I write complemented form of all these variables for this case, and it becomes like x bar, y bar, z bar, and OR between them. So my sum term for the very last row is x bar, y bar, z bar. Take another example, 101 maybe, 101. So 1 is x is 1 in this row, so it becomes x bar, y is 0 in this row, it is y, and z is 1 in this row, this is z bar. So my sum term becomes x bar or y or z bar. So this is how we define the sum terms per row. Then we put a symbol. Now in this case it becomes a capital M. The suffix value or indices of that symbol is a similar as of for the Minterm. So this becomes like M0, M1, M2, all capital. Now how I write the function in this case? Same fxyz, I pick up those row which has a value 0 and we AND between them. Okay, we pick up the rows which has a value 0 and we pick up the AND between them and make it AND between them, and then replace it with the max term symbol. It becomes M1 and M3 and M4 and M6, and then we make a symbol pi, which is a product in the normal algebra. So we borrow that symbol pi with a capital M, 1, 3, 4, 6. So fxyz is practically your product of max term 1, 3, 4, 6.